Everybody, this is Douglas MacKenzie with my portion of Fukushima, the disaster that never should have happened. I'm going to be talking about before the accident, an abbreviated timeline of events, the consequences of the accident, and our recommendations. Maybe things could have been done a little differently and it could have been avoided. So the situation before the accident, multiple companies and organizations sort of dropped the ball here. TEPCO was consistently pushing for profit instead of safety, especially long-term safety. The Atomic Energy Commission could have had more aggressive regulation, especially regarding the boiling water reactors. And you've already heard David talk about this. General Electric actually internally recognized the problem with the loss of coolant casualty with the Mark I boiling water reactor that they had designed. So after it was designed, a couple engineers were required to review it, and then 3 of them actually said, hey, this is not okay. We could have an accident here after a loss of coolant casualty. And General Electric didn't change anything about it, and they actually ended up quitting. 3 people ended up quitting in protest of that. So even though the risk of a tsunami was identified, TEPCO, for example, got a report that said, hey, there's been an earthquake every couple hundred years, every 100 years, and every 1,000 years. And the one that happened 1,100 years ago was really, really big and caused a huge tsunami. And we're maybe due for one of those pretty soon. So you need to beef up your tide walls. And they said, well, we don't really need to take prompt action based on this information. Meaning, hey, it happened 1,000 years ago. We don't need to do that next week. We have other stuff to think about. And there were other earthquakes and tsunamis in Japan. In fact, some of them would have gone over the tide wall at Fukushima, but the tsunamis there at Fukushima weren't really nearly as big. So they didn't think that it was a real risk, and they were using some more conservative estimates, probably so that they wouldn't have to spend extra money. So here we have a little mock-up of the reactor and then the emergency diesel generator room. The tide wall was 5.7 meters high, which means that a little water that comes over here, it can get trapped by this, and then they had pumps to pump it out. They were okay most of the time. The report said, hey, you need to double the height of your seawall pretty much from 5.7 to 10.2 meters, which of course they did not do. However, the actual tsunami on that day was 14 meters tall. So, even if they had made a bigger seawall, that might not have helped things at all, because the main thing was that the diesel generator room got flooded. The fuel tanks actually got completely washed away, and then they had no backup power. So on the day, March 11th, 2011, 1446, there was an earthquake that hit, and this earthquake was even bigger than the one 1,100 years ago. Just an unimaginably big earthquake. 9.0 on the Richter scale is 10 times stronger than 8.0, 10 times stronger than 7.0, So it happens roughly 10 times less often. So yeah, that's why these only happen, every 1,000 years. So 3 reactors immediately shut down. The other ones were already down for maintenance and stuff. And the power from the grid to the plant was lost immediately, but that was okay because they had their diesel generators. But about an hour later, the tsunami hit. It was 46 feet high, where the seawall was only 19 feet high. And, everything got flooded. They even could have made and were requested, people requested, hey, why don't you make the diesel generator room waterproof? And they did not do that either. So anyway, the diesel generators were down, and that was their only source of backup power. They had a couple air run pumps that ran off compressed air, but nothing that was capable of removing the decay heat from even one reactor. So at 2100, the government said, whoa, we need to start evacuating people, but we'll just do it 3 kilometers around the plant. You know, we don't want to make this seem like it's a huge deal, and really they didn't know how big of a deal it was. And the next morning at 6:50, going along with, you know, no one really knew how bad it was going to be. It's suspected that reactor core 1 melted through the pressure vessel at that time. We don't know exactly because we still can't go in there, because even drones and stuff that we fly in there are fried from the radiation. So at 1536, that's when the first explosion happened. The first large explosion happened with a big fire and stuff. So they had the containment was pressurizing and pressurizing and pressurizing, and they vented off hydrogen and they vented off radioactive steam, even risking explosions to do that, to try to keep the containment intact. And yeah, they failed because it exploded. And then after the explosion, well, a little bit after the explosion here at 9:40 at night, the evacuation area was increased to 20 kilometers out from 3 kilometers out. So it sort of just cascaded from there. More explosions and fires. They failed to contain, you know, all this radioactive stuff, and then they couldn't even stop it from exploding and burning. So all 3 of the operating reactors ended up melting down, you know, some of them maybe partially melting down, with unit 1 being the worst, with a complete meltdown. And we're still cleaning it up. They're thinking about building some sort of like containment structure over it, but really we don't know how we're gonna clean up from this. So here we see the water coming in over the tide wall. It even looks like it's breaking the tide wall here. And then between the earthquake and the tsunami, a lot of people died, so it's hard to tell like who died from the nuclear stuff, who died from the tsunami, or who died from the earthquake. And there's the unit exploding. A government think tank in Japan actually estimated that the total cost is going to be over 600 billion. That's in US dollars. And that's reported by Japan Times. So how would we have done things a little differently? Their main problem, it seems like, was from a design perspective. So there are a lot of reports that nitpick about this action and that action that they took on the day, but I mean, really their main thing was they were trying to use reactor coolant pumps to remove decay heat. And you really need something redundant if you want to guarantee safety, because even if it's not a tsunami, you never know if a system is going to fail. So we were trying to design something that works if the power is down and is redundant, and hopefully it'll cost a few million instead of hundreds of billions of dollars that it's going to cost to clean this up. So we thought, hey, we can just pull the steam off the reactor, condense it, and send it back. So to do these calculations, we're going to use data from TEPCO. They are compelled by international law, as is every operating reactor, to post specifications of their reactors. So you can see Unit 1 is rated at 460 megawatts. That's just the electric output. The actual heat output in megawatts is 1380. So we're going to do our decay heat calculations based on this number, 1380. And for my calculations, I went ahead and used 2 significant digits because, you know, they're pretty rough calculations anyway. So instead of 1380 megawatts, we're going to use 1400 megawatts. Their decay heat, for, you know, reactor theory reasons that I'm not quite sure of, is 6% instead of 7%. So 6% times 1400 megawatts gives us 84 megawatts of decay heat that we're going to have to remove. And this is, again, to show protection after a loss of coolant casualty. So the thing about a boiling water reactor is a loss of coolant casualty is much more dynamic and much worse because you have a water level in the reactor. So you really need to have your coolant there because the core can become uncovered much faster. The specific heat capacity of the water is 4.2 joules per gram Celsius, or since we're going to be using kilojoules, 4.2 kilojoules per kilogram. And the fire pump for our system, we were hoping that we could just roll up a fire truck and have that go to the secondary side of the condenser or cooling tower or whatever we're going to use. And that's going to pump 750 gallons a minute, which is the same thing as 2,800 kilograms per minute, or 47 kilograms per second. And we're going to use the seawater temperature. The highest one I found was 25, 26 degrees. We're going to go ahead and use 30 degrees. This is from seatemperatures.org. We're going to use 30 degrees Celsius as a conservative seawater inlet temperature. We're going to assume that the seawater on the secondary side is going to go from 30 Celsius to 100 Celsius. Of course, it's going to take more energy for that to then become steam. If it's like an evaporative condenser or whatever. But we're just going to use the energy from 30 degrees Celsius to 100 degrees Celsius, a 70 degree change. And by definition, 1 watt is 1 joule per second, so 1 megawatt is 1,000 kilojoules per second. And you guys might remember this, heat over time equals mass flow rate over time times the specific heat capacity times the temperature. So doing these calculations, we end up with 14 megawatts. So that's one fire pump that pumps 750 gallons a minute, pumping water that's going to change 70 degrees Celsius, is going to end up removing 14 megawatts of power. So we need 6 pumps, conservatively, probably more like 10 pumps, to make sure that we can remove 84 megawatts. And now on the steam side here, the design pressure, about 1200 psi, is 8240 kilopascals. And whenever steam is at 8240 kilopascals, it's going to be at 300 degrees Celsius. So the specific heat of the steam, when it's in these conditions, is 1.3 kilojoules per kilogram Celsius, which you might notice is significantly lower than the water. So I had to use steam tables for this, so we got to change the pressure from kilopascals to bar. So 1 bar is 100 kilopascals, so 8240 kilopascals, 2 significant figures becomes 82 bar, or bars. And this is a good thumb rule: 10 bar equals 5 kilograms per cubic meter of steam. And this works with precision up to about 30 bar, and then to 2 significant digits it should work up to 80 or 100 bar. So doing these calculations, we end up that the steam is going to be 41 kilograms per cubic meter, and that's just the density of the steam. The steam is going to go from 300 Celsius coming off the reactor to 100 Celsius when it condenses. And of course it's going to take additional energy to actually condense, but we're just going to assume a change of 200 degrees Celsius. And so how much steam are we going to have coming off of the reactor to actually remove the decay heat? Q equals MC delta T. Well, M equals Q divided by CT. So we're going to have 84 megawatts, or 84,000 kilojoules per second, times the specific heat capacity in Celsius, divided by the specific heat capacity in Celsius, and then the temperature. So we need to condense 320 kilograms per second of this steam. And what's the volume of that steam? It's going to be 7.8 cubic meters per second. So we need 6, maybe 10 fire pumps that pump 750 gallons a minute. And then we're going to need to condense 7.8 cubic meters per second of this steam. In an ideal system, this is the volume of steam that needs to be condensed. So can we condense this amount? Looked at a bunch of products and looks like yeah. We originally pictured sort of a large cooling tower, the type of which they already have at Fukushima and many plants. Those are more for smaller temperature changes, and they always operate. A dry cooling tower or an air-cooled natural draft tower seem to be the best option. Some or most of these require no power, and they just use air to cool the water or steam that's going through it that condenses, and then you sort of catch it and pump it back. One sort of efficient option could be using a condenser, but these run off of electrical power, so we would have to have another source of power, which kind of goes along with the same problem that they had with the reactive coolant pumps. So an evaporative condenser was also a good option. Takes a lot less power than a condenser, and even though it has some of the internals of a condenser, it also has cross flow in there like a cooling tower. And so one of the notable things about this type of evaporative condenser is that it can operate with no real loss after just sitting there for a long time, which is what this would have to do, of course. We're not going to be using this all the time. This would be used only for testing to make sure it's working, and in the case of like worst case scenario. So basically anything that sort of goes along with our traditional concepts of reactor fill that then keeps the core covered and then removes the decay heat would have been able to work to prevent this disaster. But the problem was that they just had emergency decay heat removal that was from the diesel generators with reactor coolant pumps. So of course many other systems could have removed the decay heat, but ultimately it was a design flaw that they didn't have any redundancy. Alright, so for references, the BBC quoted a geologist to talk about the 1,000-year event. 1,100 years ago was the last time there was a big earthquake like that, and that was right after the disaster. This guy was talking about air-cooled condensers, and then the real cost of the Fukushima disaster, again from a government think tank reported by the Japan Times. Seatemperature.org gave me the seawater inlet temperature around Tokyo, and then TEPCO posting its own specifics about the reactor. So thanks guys for your time, and have a good one.